Today we discuss unit number 4 assembly modeling. These are the topics to be followed basic of assembly modeling, purpose of assembly modeling and its disadvantages top to down, bottom of assembly modeling approaches, analysis clearance, undercut, interference stack up analysis, cumulative effective of tolerance in after assembly condition, then motion analysis. These are the topic to be covered for the unit number 4. So the basics of assembly modeling. So combining multiple parts using constraints to create a complete product. So what is the assembly modeling? The assembly modeling is the process of combining two or more parts components using constraint to define the relative position and the motion of the form to complete the product or mechanism. So benefits of assembly modeling: design a complete product, visual the how parts work together as complete system, check fits and function, detect interference and ensure the proper alignment and motion, improve the productivity, reduce cost, generate build of material, then support documentation. These are the benefits we are used to assemble by the modeling process. The components of an assembly. So, for example, to be is made of multiple parts, sub assemblies, and standard communications. So, for these diagrams are clearly shows a number of parts of the assembly component by the for example of the product. So, like bolt, bearing housing, then pulley, shaft, collar, washer, then base plate. So the types of component is in an assembly. So part, sub-assembly, standard component, then virtual component. Part, a single 3D model used in the assembly. Sub-assembly, an assembly that it is used in component in a higher level assembly. Standard component of the shell part like bolt, nut, washers, bearing, etc. Virtual component created within the assembly environment without an external file in some CAD. So component constraints match coincident, concentric, parallel, perpendicular, tangent, and distance. Typical workflow of assembly modeling: start new assembly, create a new assembly file, and set units. Insert component, add parts, subassemblies of started components, apply constraints, use matter to define the position and alignment, check and validate. So check the information's clearance and motion, check finalize the assembly, save assembly and generate a drawing, then bill of material. Types of assemblies: bottom up, top down, and hybrid assembly. Explained views have to be showed from the visualization, assembly instruction, and the documentation. Interference checks: no interference, then interference checked. So application: so automotive, aerospace industry, mechanical industrial, then consumer products, then robotics, then medical devices. Advantages of the assembly modeling: so improve design accuracy and reliability, enables better visualization and communication, reduce physical prototypes and development time, helps in motion simulation and mechanism analysis, facilitates easy modification and updates, supports downstream process like drawings, bill of material and manufacturing. Then assembly modeling purpose, advantages, and top-down approach. Purpose of assembly modeling combines multiple parts using constraint to represent how they work together as a complete product or a system. So represent a real-world product of mechanism, define the relative position of the motion of the part, check fit, function and interference between the component, generate drawing, bill of material and supporting function, improve the collaboration between design analysis and production. Advantages of the modeling: improve design accuracy, time saving, cost reduction, better visualization, easy documentation, support downstream process. So top-down approaches in assembly. So master assembly, key features: sub-assembly for the housing, sub-assembly for the shaft pulley, sub-assembly for the bearing unit, and sub-assembly for the fastener. So these are the example of the fasteners for the assembly in design interior. Then create master assembly, then create layout, then create component, then apply constraint. This is the workflow of the top-down assembly. So finally checklist and finalize the document. So applications same as automotive, aeronautical industry, robotics, and apply home places and infrastructures. Then bottom-up modeling approaches: building an assembly by creating individual part first, then and then assembling them. So what is bottom-up modeling? Each component is designed and modeling individual Parts are created based on the requirement drawing or specification. After all the parts are ready, they are assembled using constraint made for the complete assembly. So the key idea creates the parts first assembled layer. So bottom up modeling workflow, create individual part, save part in library, insert part in assembly, apply constraint, adds, check, validate the finalized assembly. So advantages: part can be created, tested individual, easier to manage and modify the individual component. Parts for the multiple assemblies allowable parallel work, then better control over part details and modification. Changes one part automatically update in the assembly. Suitable for standard parts in libraries. When I to use bottom-up approach, when all the components are known in advance. Adage when the parts are complex and needed detailed design. When part will be reused in multiple assembly. When the work within the standard company component. When the parallel design by a team is required. Component liberal library for the example, bearing shaft, pulley housing, base plate, bolt, nut, and washer. These are the examples of the bottom-up modeling approaches. So the typical application: machine design, automotive, then industrial equipment, consumer product, and robotics. So important constraints: so constraint, coincident, concentric, parallel, perpendicular, tangent, and so distances. Analysis of the clearance. So the clearance, it is ensuring the proper fit and function and safety in assembly. What is the clearance? So the clearance is an international space or gap between the two parts in an assembly to allow the relative motion assembly easy assembly on the prevent interference during the operation. So ensure smooth movement, prevent interference and wear, accommodate manufacturing tolerance, improve the product reliability and life. Types of tolerance: reliable clearance, axial clearance, angular clearance, and end clearance. Why the analysis clearance? Prevent interference, ensure functionality, accommodate tolerance, improve the reliability, ensure safety. Then methods of analysis clearance: CAD interference check, motion simulation, section analysis, tolerance startup analysis. Clearance analysis workflow: define the requirement and the build assembly, assign motion, then run interference check, evaluate result, and optimize and finalize. Example of the concentric rod, connecting rod to crank assembly. That is examples to show for the interference clearance check for the value of 0.35 mm. The typical clearance requirements for the application: shaft, piston, gear tooth, slider in guide, and face-to-face. Best practices: always define for the minimum acceptable clearance, consider duration, manufacturing tolerance, and thermal expansion. Check clearance at all the position in the range of motion. Use simulation, easy to design the process. Document, validate clearance requirement. Benefits: the better product performance, product reduced failure, lower maintenance, cost saving, higher customer satisfaction. So these are the analysis of clearance by using the safety in assembly section. The undercut. So undercut and overhanging geometry that cannot be manufactured or assembled in the straight direction. So what is an undercut? It is a portion of part that is not directly accessible by the tool, mold, and the matting component in a straight line of the action. So example of the undercut: an internal groove, recess, hole with shoulder, hook, and snip nature. Why undercuts are problem? The manufacturing difficulty, increased cost, longer cycle time, assembly, disassembly issues, the functional risks. How to identify the undercuts? Visual inspection, draft, full direction, CAD analysis tools, then sectional view. Solutions to handle the undercut: provide a draft, change design, use the side actions, use collapsive curve flows, then split the part. Then example: good or bad design. Design for the undercut, it is in the inside of the material, so it is a bad design. Good design, it is a no undercut inside the component. So the best practices: always design the tooling, matting, direction in mind, use the adequate draft angles, and avoid the unnecessary undercuts. Consulting the manufacturing early in the design process, validate the design using CAD analysis tools. So the main thing: undercut the increasing complexity, cost and risk, good design, and eliminates simplifying undercuts to ensure the easy manufacturing assembly and reliable performance.